Yeah. Here I will discuss the concept of decreasing rearrangement. Uh, Formally speaking, we define a decreasing rearrangement for a measurable function defined in some sigma finite measure space, and we do it like this. First, we consider the distribution function, the tilde distribution function, the distribution function of the absolute value, and then that's how we define the function f star, which is called decreasing rearrangement, and it is called the decreasing rearrangement associated with the original function f. And that's the definition of it. So we take the infimum of all those non-negative values y, such that the distribution function, tilde distribution function, is less or equal than x. We will study the properties of this function probably in the next comments, but here I will give just one example, which explains to you what this concept is about. So I'll take the function sine x over the segment 0 to pi, and I will assume that the function is 0 elsewhere. Sine x over the segment 0 to pi. Now, because it's a two-stage construction, of the decreasing rearrangement. First, we have to realize what's the distribution function of this will be. So here's the absolute value function, absolute value of sine. Here it is. Now, I have to find the measures of those points where my function given bigger than given number x. If this is my line x, this is the level 1. If this is my line x, the set of points where my function larger or bigger than this x, it will be this segment and this segment here. These blue segments, they represent those points where my function larger than given number x. So coordinates of these points, the coordinates of these points, they are, if you solve for this, one of them will be arcsine, the other will be pi take arcsine x, and these ones will be pi plus arcsine x, and this will be 2 pi take arcsine x. Now, the distribution function of point x, it returns the length of these two blue intervals, and that's very easy to compute this length. The distribution function so ends up to be like this over the segments 0, 1. If I give you the graph of this distribution function, here's a graph of the arcsine, or in fact 4 arcsine. Now, this is a point 2 pi, this is a point negative 2 pi. If you use this graph, if you flip it over, and if you construct this function, the distribution function, here's my distribution function. The function is not defined to the left of the origin, because if you take this line x somewhere here, the measure of those points where function larger, where it's absolute value larger than this line, it will be the whole real line, which doesn't have a finite measure. That's why your distribution function starts from the origin, where you do have values, because it's strict inequality here, and that's the distribution function. Now, if you try to construct the decreasing rearrangement based on this distribution function, then you have to analyze this inequality. If you analyze this, and if you use the expression we found for the distribution function, you will have with inequality like that. You can quickly solve this into something like this. And now, using the fact that sine is the increasing function, and one of the identities for sine and cos, we end up with something like this. Now, this inequality turns out to be equivalent to this inequality. If you take the infimum of all those y's, you will end up with the expression for the decreasing rearrangement like this. And that is the decreasing rearrangement of this function. Here it is. It is the decreasing rearrangement. If you try to compute the distribution function of this new function, so if you just take this line and this line, and if you ask how many points you have above this line, that's how many points you have above this line, above this level x. If you solve for this, solution will obviously be something like this for arc cos x, which we know identical to this, and we see this is 0.2 pi, and we see that the distribution function for the decreasing rearrangement is identical to the distribution function of the original function. So, see, the decreasing rearrangement, at least from this construction, you can see that this is a function which, on the one hand, has the same distribution as the original function, On the other hand, it has one extra property. It is decreasing. So informally speaking, what happens, you take all of these points, all of this area under your graph, and you sort of reshuffle it such that the highest columns here, they go first. So you see the highest, and the lowest ones, they all get shuffled into the end here. And that's the informal description what the decreasing rearrangement is, and that's the explanation. Actually, it also explains the term decreasing rearrangement. It's a decreasing, and it is a rearrangement of the area under the graph of the original function, of the absolute value of the original function. One of the consequences of this observation is actually that if you compute moments of your original function, this, due to very simple observation and due to a very simple result we proved in my earlier comments in relation to distribution function, this will be identical to the moment of decreasing rearrangement.